All right, so in the previous example, this is a continuation of example 2, we had the function y equals 2x, and we found that the area underneath y equals 2x is approximately 2 over n squared plus 4 over n squared plus 6 over n squared plus dot 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 plus 2n over n squared, where n represents the number of rectangles that we decide to use. Now, let's say we decided to use 2 rectangles. What is that going to look like for our approximation then? So if we use 2 rectangles, then the base of each rectangle would be 1 over n, which is going to be 1 over 2. So, we're going to have two rectangles of equal width, and I'm going to draw one like this, and then I'm going to draw another one like that, and there's a lot of area above the line y equals 2x, and what ends up happening is we're going to be overestimating a good amount. But let's see. So if we evaluated 1/2, the height of this rectangle is going to be 1 because I'm taking this number and multiplying it by 2. And then the height of that rectangle is going to be 2. So 1/2 plus 2 is equal to 2.5. Now remember, the actual area is equal to 1, so we're 1.5 units over. So how could we make this more accurate then? Well, it turns out that you get more accurate the more number of rectangles that you use. So what if we used n equals 5 as the number of rectangles? Well, then each rectangle would have a base width of 1/5 or 0.2. 1, 2, 3, 4. So this would be 0.2, 0.4, 0.6, and 0.8. And now our rectangles would look something like this, and we pretend those are all evenly width. My drawing is kind of poor, but now there's not as much area above, and so let's use the approximation formula that we had here. So a sub 5, the area with 5 rectangles is going to be equal to 2 over 25 plus 4 over 25 plus 6 over 25 plus 8 over 25 plus 10 over 25. And if you add all of those together, you get 30 over 25, and that is equal to 1.2. So a sub 5 is 1.2. That's our approximation if we use 5 rectangles. Remember a sub 2, that was 2 over 4 plus 4 over 4. So that's 1.5. I think I miscalculated it earlier. I think I said I got 2.5 maybe. So notice that this area is closer than this area because we're using more rectangles. So let's do a sub 10, and that's going to be 2 over 100 plus 4 over 100 plus 6 over 100 plus dot dot dot, and then our last term is going to be 20 over 100. And if you add up all of those terms, that is 1.10, which again is even closer than our first two approximations. For if we used 2 rectangles, we got 1.5. If we used 5 rectangles, we got 1.2. And then if we used 10 rectangles, we got 1.1. What if we used 100 rectangles? So that's going to be 2 over 10,000 plus 4 over 10,000 plus 6 over 10,000 plus dot 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 plus, and then our last term would be 200 over 10,000. And if you add all of those together, that ends up being 1.01, which is very, very close to our exact area of 1. So it turns out the more rectangles that you use, the more accurate your approximation is going to be. Now, you might be asking, Mr. Kwan, how do we find this sum? That seems like a lot of terms to add up and a lot of work. I don't want to punch in every single term like that into my calculator. Well, there's a really nice trick to going about doing this. And the first thing that you want to do for a sub 100 is all of the numerators are even, so you could factor out a 2, and then what you'll be left with is 1 over 10,000 plus 2 over 10,000 plus 3 over 10,000, and then the last term is going to be 100 over 10,000. So essentially what you're doing, if you look at the numerators, you are trying to add up 1 plus 2 plus 3 plus dot 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 plus 100. So basically you're trying to add up all of the integers between 1 and 100. And there's this famous story in math where the famous mathematician Euler in 3rd grade had a teacher that didn't want to teach the class, so he gave this 3rd grade class the task of adding up the first 100 integers. And there's a famous story, who knows if it's true or not, but basically this famous mathematician Euler calculated this sum very quickly. And the way that he did that was he noticed that if you reverse the numbers and then add them with those as well. So you can add these up vertically. So 100 plus 1 is 101. 99 plus 2 is also 1. 98 plus 3 is also 101. And then 100 plus 1 is also 101. And the number of terms here that we have, there are 100 of them. So basically we're doing repeated addition. And so we're essentially calculating 100 times 101, but then we basically doubled the number. So then we have to divide it by 2. So let's see, what am I trying to say? So if you were summing the first 100 numbers, that sum would be 10,100 divided by 2, which ends up being 5,050. And you can generalize this to the sum of the first n numbers or whatever. And so here, this ends up simplifying to 2 times 5,050 over 10,000. And that's how I ended up calculating it in the calculator. So if you throw that into your calculator, it ends up being 1.01. So in general, if you have 1 plus 2 plus 3 plus dot 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 plus n, the sum of the first n integers is the n value times 1 more than the n value and then divided by 2. So this is an important formula to know. So this really concludes this example where we have approximated the area under the curve. So, our best approximation was here with 1.01 when we used 100 rectangles.